So uncertainty is the degree of doubt in a single measurement and uncertainty is where significant figures or the number of meaningful digits, the number of meaningful digits is applied. And the number of meaningful digits then is determined by what measuring device you're using. By the measuring device you are using. So you'll see I have a ruler right here. And the ruler has definite marks at 6.4 and 6.3. And that last one is just an estimate. You'll notice it looks like it's right in between 3 and 4 if you look really close there. And that's what significant digits is all about when you're talking about taking measurements. So I've put in significant figures when measuring consist of all the digits known to be certain plus one final digit, which is estimated. So when you're taking measurements, you estimate that last digit. And when you're looking at data that's a measurement, such as this here 6.35, then that automatically tells you the 6.3 was certain, it was on the equipment, and the 0.5 is just the estimate. So you could have several people take this same reading, and some might get 6.33, some might get 6.34. It may be different on how they estimate that last digit. So it is an estimate. So your rules for determining significant figures. These rules may seem a little overwhelming at the moment, but we're going to practice this in class as well, and you'll have this to refer to, but practice really does make perfect here. So the first rule is that zeros appearing between non-zero digits are significant. Okay, so zeros between non-zero digits are significant. So that one has 3 significant figures. 87,009 has 5. The next rule, zeros appearing in front of all non-zero digits are not significant. So you're going to go all the way over until you hit an actual number and then count after that. So you'll have 1, 2, 3, 4, 5 significant figures. This one you're going to go all the way over, and that's going to be your first non-zero digit, and therefore you just have 1 significant figure. The next one are dealing with zeros at the end. Zeros at the end of a number, and, look at this and, it's important, and to the right of a decimal point. It's got to have that decimal point to be significant, are considered significant. So 85.00 has 4, and 9 and 9 zeros, I think I counted that correctly, has 10 significant figures. Now lastly, if you're dealing with zeros following numbers and to the left of a decimal point, that may, if there's no decimal point that exists, just an implied decimal point, then you can have, in this example here, this could have anywhere from 1 to 4, depending on how many are placeholders, as indicated by a line over the last significant digit, or by the decimal. So 2,000 just has one significant figure. 2,000 with the line over the second 0 has two significant figures. And 2,000 with the decimal place has four significant figures. Now, I'm going to have an alternate set of rules for you to put in your folder that may work better. These may seem a little bit long and lengthy, but I have a song and maybe a simplified version of the rules that may help you. So just remember that those are coming, and you can use whatever set works best for you. When you perform calculations with measurements, you have to know how to handle significant figures, especially when using a calculator. Especially when using a calculator. We want to avoid calculator vomit. That is bad. Okay, what it looks like is this. You get this very long answer. It contains digits that just are not justified by the measurements used to calculate it. So an answer has to be rounded off to make its degree of certainty match whatever the original measurements were. So the answer should be 0.471 in this case, because you had three significant figures measured by the grams taken there, and 327 milliliters and whatever they were measuring there. And so the final measurement really needed to be cut off right there to match the accuracy of the measurements taken. Our next little section here is scientific notation, also known as exponential notation. You should already be familiar with this and good at this, but just in case, a little review here. It involves the representation of a number as a power of 10, and then numbers are written in the form, M, it's a capital M, times 10 to the n. And I show you that because I actually have seen this show up. I have seen that show up several times in some of my chemistry stuff in college. And you need to know what you're looking at when you see that. So M times 10 to the n, where the factor M is a number greater than 1, or greater than or equal to 1, excuse me, and the correct amount of significant digits, according to what the measurements were, but, excuse me, less than 10, and n is a whole number. So the rule is to convert a number to scientific notation. The original decimal point is moved either to the left or the right so that the final number includes one digit to the left of the decimal, followed by however many digits to the right necessary to achieve the correct significant digits that we were talking about. And then having the exponent signifying the number equal to the number of places from which the original decimal point was moved. So here are your examples. If you've got 2,300, its exponential notation is 2.3 times 10 to the third, or you'll see it on your calculators and in some references 2.3e 10 to the third. So your decimal point started out here. You had to go here to get your M factor correct, greater than 1 and less than 10. And so to get back to where you started, you have to jump 1, 2, 3 spots to the right. That's how I work with that. Your brain might process that differently, but that's what works for me. And the same here. I go to where I ended up, which was right here. And then I look at where I started and figure out how I had to get from here to there. And so in this case, I have to go back 3 places to get where I started. And so 2.3 times 10 to the negative 3 is the scientific notation there. You may, if you have a problem in some of the calculations that we do, this sometimes will be, what causes you the biggest trouble is dealing with how to use scientific notations in mathematical operations. So let's review real quick addition and subtraction. The values of the exponent 10n must be the same. Okay, it doesn't necessarily matter which way you go with them, but they've got to be the same. If they're not, adjustments have to be made. So that they are equal. And of course the adjustments would be using what you learned up here, or what you already know about moving the decimal point and how that impacts your exponent. So once those exponents are equal, the m factors can then be added or subtracted. There we go. It wasn't letting me write. Here's an example. You need to make sure you understand how to do this. If not, you might want to practice a few times and even ask me for more practice if you're not getting enough. Okay, so we've got 4.2 times 10 to the 4th. And then we've got that added to 7.9 times 10 to the 3rd. So people are tempted just to go on and add 4.2 and 7.9. That's not going to work. These have to be the same. And so if you'll look over here, we made adjustments. I decided to go 10 to the 4th. That's just what worked for me. And so since this was the 3rd to start with, it was going to be 7900 if we just wrote it out. And so if I need to make it 4 hops to the right, I'm just going to move the decimal point over here. So now if I move it 4 hops to the right, it's still 7900. And that's just kind of how I double check whether I've got my exponent correct or not. I will write them out sometimes completely just to make sure that I've done exactly what I need to. And then your last thing is to just check the significant digits. This should only have 2 since your original measurements only had 2. So you round to the 2. And the final answer then is going to be 5.0 times 10 to the 4th. Multiplication, the m factors are multiplied and the exponents are added. Exponents are added, which to me is actually a little bit easier. You don't have to do those adjustments to get those to work algebraically, following the integer rules for addition. Now that's what hangs up some people. They forget the addition and subtraction if you have a negative and a positive number like this. Okay, so don't forget that. If you add 6 plus a negative 2, it's going to be 4. Okay. So you have here 5.23 times 10 to the 6 times 7.1 times 10 to the negative 2. So you can go on and multiply these. And then you will be adding the 6 and the negative 2. So your final answer, once you consider your significant digits as well, is going to be 3.7 times 10 to the 5th. Don't forget the units also have to be squared and cubed. Or cubed. It's cubed if you're multiplying 3 times, of course. Okay, and division is very similar. The m factors are divided, and the exponent of the denominator is subtracted algebraically. Oops, I've already got algebraically down. Following integer rules for subtraction. And again, if somebody's going to mess up, that's probably where they're messing up. So with our example here, you're going to divide these two. And you'll get that big long calculator vomit that you'll deal with when you round things off. So you'll adjust the correct significant digits. You can do that at the end, but it's easier to get them out of the way here. And then you're going to subtract the denominator exponent from the numerator. So 6 minus 2. And one thing people need to remember is that you have to add the opposite when you're subtracting integers. So it's actually 6 plus 2 equals 8. Now, if this integer addition and subtraction is not something that you're very good at, or you have forgotten since you haven't been using it regularly, this is a good little website to go to, or anything similar that's a math help site for help at reviewing, adding, and subtracting integers. You definitely need to be good at that. So we put all this together and we get 0.74 times 10 to the 8th, but that's less than 1. Remember, it needs to be between 1 and 10 to be correct scientific notation. So we just move the decimal place one spot over, and so it goes from being 8 to 7. So now it's 7.4 times 10 to the 7th. And that's going to be all for now. We will pick up dimensional analysis in our last video. It's rather lengthy as well. And so just make sure that you know how to add and subtract your scientific notation, your exponential notation, and that you understand significant figures. And let me know what questions you have.